review of some material from the 1950s in cohomological class field theory. But I'm going to, at some point, switch to a slightly different perspective because I want to emphasize the question of making things as canonical as possible, and that will require a slight change in language. But we're going to start with something very classical. So, definition. So, a class formation is a pair gamma A, where so gamma is a profinite group. And two, so A is a discrete gamma module. So just a abelian group, abstract abelian group with a continuous action of gamma. And what that means, it's basically equivalent to, is that every element in A is fixed by some open subgroup of your profinite group gamma. So, okay, that's the data, but then there's the axioms, and they're very, very easy to formulate. They concern group cohomology, such that for all, so there's a situation which is n is in H is in gamma, so this is just an open subgroup, but this is open and normal in H. In practice, gamma is going to be the absolute Galois group of a field. This will correspond to a field extension, and then we have a Galois extension of that field extension of our base field. Okay. So then, in this situation, something happens in group cohomology. So we take the n fixed points, which has an action then of the group H mod n, and we ask something for the H1. I'm going to use the standard notation for it. So this is a group cohomology. Yesterday I was putting a B in front to indicate that it's group cohomology, but today we're being classical and I won't do that. So this is a group cohomology of this group acting on this abelian group here. So we want the H1 to vanish, and we want the H2 to be cyclic of order the index of n and H, so the order of the group that's acting. Okay. So that's a very concise definition, and there's two things that should be explained about the notion of class formation. The first thing is that is how you can check the axioms in practice, and the second thing is what consequences do you get from the axioms. And let me start with in fact, the consequences are many, but let me start with the most basic one. So the basic consequence is comes from a famous lemma, Nakayama-Tate, concerning cohomology of finite groups. So suppose G is a finite group, and A is a G module. So now it's just an abelian group with an action of G. And then suppose we're given a class in H2. And we make an assumption. So if you're given a class in H2, then you can cup with it on cohomology. So you would get a map from cohomology with Z coefficients to cohomology in 2 degrees higher of with A coefficients. And you get not just a map like that in ordinary cohomology, but also in Tate cohomology. And we want to assume that this map is injective in degree, such that there exists an I0 in Z for which this is injective in degree I0 plus 1, an isomorphism in degree I0, and surjective in degree I0 minus 1. Okay, that's the hypothesis. And the conclusion is, oh, sorry, we want to assume that not just for G, but also for all subgroups. And same for all subgroups. In other words, so if we take our U, we can restrict it to a cohomology class in H, and we can take H-Tate cohomology for any subgroup H. And we also demand with the same I0, that's not so important, but that we have the same hypotheses of injectivity, bijectivity, and surjectivity. Then this cupping with U is an isomorphism in all degrees. For all subgroups.
So we require this for open, H open, right?
G is finite.
Oh, sorry, yes.
Okay. So, right. Let me give you the sketch of the proof because the ideas will be relevant to many things we do.
Sorry, so far there is no relation to definition before?
I'm just explaining a beautiful lemma in finite group cohomology. Patience. Okay, so here's the sketch of the proof. So this is a class in H2, G with coefficients in A, but there's another interpretation of that. It's an X2, say over the group ring. Of ZA. And we can represent it by a map in the derived category. And then let M be the object in the derived category, which is the shifted mapping cone, the fiber of this map U. Then the hypotheses give that now that the Tate cohomology of H acting on M, so Tate hypercohomology, I guess I should say, of H acting on this two-term complex M is equal to 0 for I equals I0 or I0 plus 1 for all H subset G. And we want that this is equal to 0 for all I. So we've translated the problem to saying that we have now an object, just a single object with a G action, and we have Tate cohomology vanishing in consecutive degrees for all subgroups, then the object has to vanish identically. And now it no longer matters that M was built in this way. It's just a pure fact about objects in the derived category with G action.
So by the way, for the definition of Tate cohomology, well, at least in some references, it's a bounded complex, but is it possible to define it nicely for?
Yeah, it's possible to define it nicely for an arbitrary complex.
Okay.
Yeah. Allow me to not explain the details. It's just there's always a map from the homology to the cohomology given by, but we will only ever apply it for bounded complexes. So allow me to not give the explanation of why it makes sense in general. Okay. So there's some standard reductions. So use the transfer maps. So you can localize at a prime and then use transfer maps to reduce to CELO subgroup. So you can assume that you have a P group and then use the standard induction on the order. So every P group has a filtration where the quotients are cyclic of order P, so reduced to cyclic groups. And then the key point is that this Tate cohomology for G cyclic, this Tate cohomology of anything is a module over the Tate cohomology with Z coefficients, and this is 2 periodic.
So how does the reduction on the order of the group go? So if you know it for all proper subgroups, or you know it for...
Let's say you know it for every group of all proper quotients. Let's say you know it for all proper quotients. So then by this case, so you have a central cyclic group of order P in there, then there is a little triangle, distinguished triangle you can make building up the Tate construction for G in terms of the Tate construction for the cyclic group, and then Tate construction of something acting on the quotient. And you, I mean, I don't know if I can produce the details immediately, but there exists an argument. It's not too difficult. Right. Okay, so yeah, the point is that this is calculated by a resolution which can be used to prove, the standard resolution which can be used to prove that it's always 2 periodic. But it's a ring, and it's acting on this guy, so this guy is also 2 periodic. And then if you have something 2 periodic which vanishes in 2 consecutive degrees, it has to be identically 0. So that's the point. So now let's apply this to class formations. So there's a little lemma. So if CA is a class formation, then can choose. So I said in the axioms of a class formation, I said this group was cyclic of a given order. And the lemma says that you can choose reasonable generators that are reasonably compatible. So it can choose so UHN so for all HN is above, such that, so if you restrict U, you get U prime. I'm going to use obvious notation here. So if you have a situation like this and you restrict U, you get U prime. But also, if you inflate U, this time you don't get U prime because that wouldn't make sense because the groups, well, but let's say, so we're, yeah, the index of n in n prime times U prime if n prime is contained in n. Okay, so there are some, so when in this situation here, your group is getting bigger, so it wouldn't make sense that you have a generator for a smaller cyclic group and you put it in a bigger group, that it would still be a generator, but it would make sense that it was exactly this much times a generator, and that's what you require.
So it's a use axiom of choice here.
No.
You can choose.
Yeah, there exists. So we will be more precise about exactly what it takes to. I'll describe exactly the set of all choices later, but at the moment, just yeah, existence. Okay, so now we do this. We make this choice. Then by the Nakayama-Tate, so we have this UHN, and it's quite easy to check that the hypotheses of the Nakayama-Tate lemma are satisfied in degree 0 and -1 or degree 0 and 1 or something. Well, you can easily find from the class, from the axioms of the class formation that the hypotheses of Nakayama-Tate are satisfied, and the conclusion is that if you look in Z, sorry. So the Tate cohomologies of Z with the trivial action and your thing you're interested in just differ by a shift of 2 for all subgroups. And now the relevant degree you want to take is I equals -2. The definition of Tate cohomology is such that in positive cohomological degrees, you're seeing group cohomology. In negative cohomological degrees, you're seeing group homology. And in degree -2, you're seeing H1. And H1 is just the abelianization of the finite group under consideration. So you get a natural isomorphism like this. And then when I equals -2, this is equal to 0. And the Tate cohomology in degree 0 is just, you take the group and you modulo the transfer map that you have from the H fixed points. The other way around, yeah. You take the fixed points for this group acting on that, which gives this. And then there's always a summing over the action of the group. Gives a transfer map from n fixed points to h fixed points, and you take the co-kernel. That's the definition of the Tate H0. So you get maps like this. And you can just as well view them the other way around because they're isomorphisms. But when you view them the other way around, the compatibility properties, compatibility under inflation, it turns out, implies that you can take the limit over n. And what you get is a map from AH to the abelianization in the profinite sense of this profinite group H. And this is the so-called Artin map. And it's got dense image. And the kernel is the so-called group of universal norms. So take the intersection of the transfers of all open normal subgroups. So this, because it's dense image and you have control over the kernel, basically this says you completely understand this group in terms of this group and this system of transfer maps. And also those compatibility properties on the so-called fundamental classes there, they also show that these Artin maps satisfy various compatibilities as H varies, which you can imagine. So you have both natural maps and transfer maps on both sides, and they're the only commutative diagrams that make sense to write down are commutative. Okay. So that's pretty cool that, okay, you start from some very simple axioms in group cohomology and you end up with basically the conclusions of class field theory, or how to describe the abelianized absolute Galois group. That's in practice the abelianized absolute Galois group in terms of some modules that you can just write down as long as you can just verify some cohomological axioms for those modules. That's pretty cool. But how do you verify the axioms? Well, it turns out that can be reduced to some cases where it just becomes some very concrete things you check in a given situation. So how to verify, so criterion. So suppose gamma A satisfies. So the first axiom is going to be, okay, so let's say, so for axioms 1 and 2, it's going to be for all h and n such that h mod n is cyclic. So by some reductions, you more or less reduce to checking the axioms in the case of cyclic extensions, similar to reductions to that we had in the proof of the Nakayama-Tate lemma. And the advantage of cyclic extensions is, again, that the Tate cohomology is too periodic. So instead of trying to understand H2, which is what we have to do to check the axioms, we can just try to understand H0. And H0 is completely elementary. You can phrase it without cohomology. So, and the other advantage of the fact that it's too periodic is that there's a number that's easy to calculate. And that's, so you only have two things to understand, the H0 and the H1, right? And maybe individually they're tough to understand, but in general they're going to be finite. I mean, not in all complete generality, but in examples they're going to be finite, and the quotient of their orders is going to be easy to calculate because it behaves like an Euler characteristic. It's going to be multiplicative in short exact sequences, again as a consequence of this twofold periodicity. That quotient is called the Herbrand quotient when it's defined. So let's just denote it H0 mod H1. So in this case, you'll want to calculate that the Herbrand quotient is equal to what it's supposed to be. Or should it be negative? No, yeah, it should be that. And then 2, you can check either that the H1 AN equals 0, and then you'll definitely know that things are as they should be, namely the H0 will then have to be of this order, which by 2 periodicity is the same as the class field axioms over there. Or you could check that when you take AH mod transfers of AN, you have to check that this is not too big. So if this is less than or equal to the order of H mod n, then again, by inspection of this, and then you would conclude that this happens and you have equality. So on cyclic extensions, you just have to calculate the Herbrand quotient, and then you have to verify that there are enough norms. So in practice, A is here, I'm thinking of it as an additive group, but in practice it looks more like a multiplicative group. So this transfer is more like a norm. So here you just have to verify that you have sufficiently many norms to make this group small. Yeah, it's not so bad. Okay, and then the third thing you need is that you need enough cyclic extensions. I'm going to be vague in this one, but such that you have equality. In 2, yeah. Wait, doesn't, yeah.
No, but if you assume 1, that the Herbrand quotient is H mod n,
yeah.
And if you have the either or, then in fact you know
yes.
that the 0.
Yeah, you're right. So let me just say you have enough cyclic extensions, because you're right that that's automatic. So maybe I'll even say it precisely. So for all H and all say n in n, there exists a cyclic. There exists an n normal in H with H mod n cyclic of order n.
But n is not 0.
N is yeah. Yeah, n is non-zero. Right. So if you have enough cyclic extensions, then you can, there's a method of forming you have an arbitrary guy, you want to make sure that the thing is big enough. There's a method of forming the compositum with the cyclic extension, and you can get the conclusion that you want. Right, so that's okay, suppose that then it's a class formation, so. All right, so now to show you that this is actually just really easy in practice, let's do some examples. So, I mean, I won't do them completely, but so let's say K is a non-Archimedean local field, and let's it's not necessary, but just for simplicity, let's say it's characteristic 0. Okay. Sorry, I lied. I want to make one point before I go to the examples. So sorry. So remark. So again, I said a theme of this lecture is going to be trying to make things as canonical as possible. And we already messed up when we gave the definition of class formation secretly, because I said in the examples, gamma is going to be the absolute Galois group of a field. But there is no the absolute Galois group of a field, because defining the group requires choosing the algebraic closure, the separable closure. And in number theoretic examples, okay, arguably for Q there's the algebraic closure inside C, but then when you talk about local global compatibility at p-adic places, Maxime will tell you a different choice, and then you'd have to compare them, and it's a mess. So really it's not that, so in examples, gamma is not well defined as a group, but only as a, I guess you could say, connected groupoid. So, okay, you could think, so it's a profinite group, so you would have a profinite connected groupoid. You could, for example, use the condensed language to talk about that, but let's not do that. Let's instead use the language of Galois categories, or equivalently, Galois category. So C would be C gamma, which is the category of finite continuous gamma sets. So kind of in Galois theory, this is the only thing that's ever really relevant anyway. The group itself, we only care about through its representations, and more specifically through its actions on finite sets. So for F a field, then instead of the absolute Galois group of F, we instead think of CF, which is the category of finite étale F algebras, which is the category of finite products of finite separable extensions. Okay.
Or maybe the opposite of it.
Yeah, maybe the opposite. Thanks. Yeah. And maybe no. Let me not take the opposite.
No, if you want it to be a Galois category.
Oh, this one needs to be the opposite. Yeah. Yeah, this one needs to be opposite. This one, no, they both need to be opposite. Thank you. The schemes, finite étale F schemes, yeah. Then it wouldn't be opposite. Yeah. Okay, then this one is opposite, yeah. Thanks. Okay. Right, okay, so I just want to start already doing things in the more canonical language. Okay, so K is a non-Archimedean local field. So then C is this Galois category. And then A, we're going to take to be GM. So in other words, so if L over K is separable, so A of L is just L cross. Yeah, so if you're, right, I should explain what A means in these terms. And then an A will correspond to a sheaf of abelian groups on the Galois category. Right. And then the class field axioms translate into saying that for all x in C connected, corresponding to a finite separable extension, and for all subgroups of the automorphism group, corresponding to the H mod n we had earlier, then you have the same axioms. Cyclic of order, the order of G. Okay. And when you're specifying a sheaf, it's enough to specify it on the connected objects, because the other ones are just finite disjoint unions of those, and part of the sheaf property is that should go to a finite product. So, okay, so then either of these descriptions tell you what the sheaf is in this case. The class field axiom, so the Herbrand quotient, let's analyze the structure of the unit group. As is well known, you can take the valuation of an element, and you get something in Z, and then what's left over is the unit group of the ring of integers. But another nice fact about the Herbrand quotient is that it vanishes whenever you have a finite G module. So G is a cyclic group. Whenever you have a finite G module, the Herbrand quotient is 0. So you can always work up to finite G modules when you're doing Herbrand quotient calculations. And because of the logarithm and exponential, up to finite groups, the multiplicative group is the same as the additive group.
At least in characteristic 0, in mixed characteristic. Okay. Okay.
Exactly why I made that assumption, even though it's not really necessary, just for ease of argument. But also, this is just some lattice inside L, And L by the normal basis theorem, so implicitly we have some cyclic extension here, but by the normal basis theorem, if you had the bottom of a Galois group, this would be the same as this guy, but there's another lattice inside there, which is OK bracket G. So again, because you can work up to finite groups, this guy might as well be the same as this guy too. But for induced modules like this, it's obvious that the Herbrand quotient is 0. Right. So here the Herbrand quotient is equal to 0 because in fact the Tate cohomology just vanishes identically. So both H0 and H1 have order 1 because it's a free module over G. So the conclusion is that this term dies, so there's no Herbrand. The Herbrand quotient doesn't, Herbrand quotient is trivial here, so the Herbrand quotient for this is the same as for this. And for this, it's an obvious calculation that the Herbrand quotient is just the order of the group. And that already verifies 1. You can see that was incredibly simple. 2 is also incredibly simple because in general for a field extensions, there's no H1 for the multiplicative group. That's Hilbert's theorem 90. So the first one is easy. The second one's actually also easy if you just study the norm map and you can make enough norms. And then the third one, enough cyclic extensions where you get equality, you can just study the unramified extensions. So that gives 1. 2 is Hilbert theorem 90. And 3, use unramified extensions. And then that's it. I mean, that's local, well, that's pretty much, I mean, then you get local class field theory. Just very easy.
So you don't have to study the Brouwer group exactly, because you need to canonifize the choices, you need some Brouwer.
Right, this corresponds to my choice of UHNs. So that, I don't, to run this argument, so to actually get the Artin map, you have to choose your UHNs, which corresponds to choosing standard isomorphism from Brouwer group to Q mod Z. We'll discuss that aspect a bit later. But abstractly, you know there exists an Artin map, and to pin it down, you need to choose your generators and such, and we will do that. But at the moment, at least you know abstractly, there exists a choice. Okay, there is one aspect that you want to be able to control this guy. In particular, you want to show that every finite index subgroup is, there's a smaller thing that is of this form. That's called the existence theorem. For that, you need to produce enough extensions, enough abelian extensions. For that, you use cyclotomic extensions in Kummer theory. But I'm not going to discuss that aspect. Okay, let's move on with more examples. So you can see this formalism of class formations. If you know your homological algebra, it just lets you reduce to some very concrete checks that you in a given number theoretic situation. Okay. So another example. Well, this one's okay. So if K is a finite field, then we can take our A to be the constant sheaf with value Z, and that's rather trivial to see that it gives you a class formation. Another example, okay, so the main example of interest will be when K is a number field. I guess I could say a global field. So then the L is going to be the Adel class group, so AL cross mod L cross. Let me just say a word about the verification of the axioms. So for one, it's a Herbrand quotient calculation, which is really not bad because of these kinds of tricks with exponential maps and so on. 2 is not Hilbert theorem 90. In fact, Hilbert theorem 90 is instead used to verify that this actually is a sheaf. So for 2, it's not so easy to do this directly. So instead you do this. So you have to make sure there are enough norms in a cyclic extension, and they come in the end from the primes that split completely. And then to build enough cyclic extensions, you use cyclotomic extensions. Enough cyclic extensions where you can control.
This second inequality
Yeah.
is to use a little bit of analytic.
Exactly, that's the easiest way, yeah.
Yeah, but apparently there are proofs which avoid this step.
Yeah, that's right, yeah.
But in Art and Tate, this is what they do.
In Art and Tate, they avoid, no, they give a purely algebraic argument.
They don't have the analytic inequality.
Right, they don't do it in the analytic way.
Ah, okay, for maybe I'm confused.
Yeah.
Just also Snöker
Uh-huh.
is related.
I mean, all the arguments are related. Yeah. Okay.
Well, and are there any other examples except class field theories? Of course, model theory should produce something else.
Oh, yeah.
You know, you have very rigid theory with
Yeah.
very many, so it should have
Yeah.
some other models.
No, yeah, certainly there are other examples. I mean,
So of course, then Cato tried to generalize local class field theory to higher local fields
Yeah.
in K groups. So
Yeah.
how close is it to the axioms?
no, yeah, it's different because the things, I mean, the relevant complexes are these motivic complexes that don't, they'll live in too many degrees for this precise axiomatics to be the correct one. Yeah, let me leave that aside. There's a modification of this example that is useful. So let's say S is a non-empty finite set of places. Of F. Then I have to define for you the Galois category. So say an L over K. Say L over K is unramified outside S. If for all places mu which are not in S, so a place of the ground field K which is not in S, and for all nu above nu, the local field extension, so L nu over K nu satisfies following conditions. So if non-Archimedean, so if nu is non-Archimedean, this should be unramified in the usual sense. And if it's Archimedean, we require that L nu, that it is not, that it's a trivial extension. Okay, so then C K S is the Galois category of unramified, extensions unramified outside S. So, for example, if S contains all Archimedean places, then the CKS is just, the usual finite étale site of spec. Then you get a ring, OKS, and it's just the finite étale site of that affine scheme. So that's one example. And another thing to note is that CKS doesn't change. the Galois category doesn't change if you add or subtract complex places. So if you have a complex place, then this condition is automatic because there's no way to get an extension of C that's non-trivial. Okay, but while the Galois category is not going to change when you add or subtract complex places, the notion of class group will change. So that's why we allow this. So then the A, which so A of L is you take L across, AL across, and then you take the product over all mu not in S of the. Okay, let me write it like this. You have L nu cross, but you want to take the norm 1 part of that. So the norm 1 subgroup of the local units, or the maximal compact subgroup of the group of local units. So in the non-Archimedean case, so this is just the ring of integers. So if this is non-Archimedean, but if it's the real numbers, then it's the plus or minus 1, and if it's the complex numbers, it's the unit circle. Okay. Okay. So then C, K, S, and this A is a class formation as well. And here it's you don't want to don't need to kind of directly verify it. You can just start with the fact that you have a class formation that it's clear that this guy gives a class formation on this category. When you just restrict to the unramified condition, which kind of corresponds to a push forward, then you get a class formation like this, and then you can check that this group is cohomologically trivial, and so then when you mod out by it, you still get a class formation.
Sorry,
Yes.
the proposal.
Yes.
We will construct examples from 3-manifold topology. Maybe not.
No, you're right. Again, no, you're right. You're right. Yes, you can. Let's discuss it. There will be a time when I can make a comment about that. Yeah. Okay. Right. So right. Okay. So but again, if S contains all non-Archimedean places, this class group has another interpretation, more scheme theoretic, I guess. You could think of it as like the compactly supported Picard group. Well, and let's say S is finite for simplicity.
It was finite always in your.
Did I say finite?
You said non-empty and finite.
Oh, I did? Okay, it doesn't have to be finite. If you take all places, then you get the previous example. Yeah. Okay, but now I want to say it's finite. So just for simplicity. So then this can be interpreted as the compactly supported Picard group. So this is Picard is really a groupoid, and you take the homotopy fiber. So it's isomorphism. So you take line bundles on this guy together with trivializations at the punctures, so to speak. And then that category doesn't have any pi1, which is why I asked S to be non-empty, and it's equivalent to this guy mapping injectively into this guy, into this quotient. And so it's really just an abelian group, and a Adelic interpretation of line bundles tells you that this is the same thing as this. And in particular, there's a useful exact sequence. So AL goes to the usual Picard group. Then you have the product of the local unit groups. Well, I guess I should say mu. So I mean, really, it's not the same S. I mean the set of places of S above the given set of places of K. Right, and then here you have the unit group. So Right. So this is another way to understand the same class group. You've got contributions from pick in units, and then you've got local units, and then this guy sits in there. All right. Where am I? Ah, yes. All right, are there any questions? Okay. So now I want to, again, try to make things a bit more canonical. So recall what we're trying to do. So we will try to, it doesn't always succeed, it will in examples, associate a Weil group to any class formation. And recall the idea that I discussed in the last lecture. So let me pretend the Galois category, again, corresponds to a field. So it's the Galois category attached to a field, and use that notation. So again, we would have some absolute Galois group is the inverse limit of all L of Galois of L ab over K. And the Weil group that you want to define will be an inverse limit of, now it's confusing, it is denoted W L over K, but it's not an analog of Galois group of L over K. It's more an analog of Galois group of L ab over K. And it sits in an extension like this. So you have this abelian kernel, and this extension should be classified by this choice of fundamental class. So that's the idea of the Weil group.
Yeah, but then of course this is defined after isomorphism.
Yeah, this is the issue. So that
Then you have to glue them together, and the point is, so you have a countable tower, or you can use some compactness argument.
yeah, that's exactly correct. Yes. So the issue is that a class in H2 doesn't really build you a group extension like this. It builds you an isomorphism class of group extensions. And that's not enough if you want to form the inverse system here and pass to the inverse limit. So you need a co-cycle level of refinement. So that would be a gerb. So what it really is an object in a two-groupoid, which is the two-groupoid of gerbs. So a gerb on BG banded by A. So those collection of such things forms a two-groupoid. Let me describe it now for you in about 5 different ways. So this is a two-groupoid. So about 5 interpretations. So one is or maybe 0 is the thing that, like, literally is a co-cycle level refinement. So an object is an x in C2 such that dx equals 0. So the kind of thing that represents a cohomology class. A one morphism would be a y between x and y would be like an alpha in C1 such that d alpha is x minus y, or y minus x. Well, you have to choose some convention about how you're going to do these things. And then a two morphism, alpha to beta, is a gamma in C0 such that d gamma equals beta minus alpha. So it turns out it's a general thing about chain complexes. You can get a two groupoid this way.
I'm not confused now. Is the A the same as the previous one, or now something else?
No, well, now I'm talking about the general situation of you have a non-abelian group acting on an abelian group. In our example, it's going to be this group acting on this group.
Okay, but the A is just the usual module.
Yeah, it's just an abelian group with a G action.
The two groupoid is not A, it's something else. No, A.
Oh, no, it is a two groupoid, where A is capital. It's the English word for like singular, indefinite object.
Yeah. Okay.
Yeah.
So the gerb itself is.
So the collection of these things forms a two groupoid. So you can't really say canonically what a gerb is. You have different choices about how to make it precise, but the two groupoid, all the different two groupoids you write down are canonically isomorphic.
So equivalent, you mean? Again, it's up to some Formalizing 3 thing.
Yeah, but when I say isomorphic, I mean what you would say equivalent for. Let's put it that way. All right. Right. Okay. So another one would be a groupoid. So X over BG. So category of groupoids forms a two category. So groupoids over BG such that the relative homology, relative H1, identifies with A. This is the closest one to the group extension point of view. So if you chose a base point, this will automatically, and such that, and the relative H0, well, so the relative pi 0 is equal to base point. Then if you fix a base point here, then X will be B of its group of automorphisms, call it W. Then W will be an extension of G by A. And that's kind of the situation here. But saying it like this is a bit more canonical. Second interpretation, we already should have known we needed to do this when we looked at the proof of the Nakayama-Tate lemma, because continuous group or just group cohomology is the same as X's. That's another interpretation of the same thing. So we also have the two groupoid of maps from Z with the trivial action to A shifted by 2 in D of Z bracket G. Or if you want to be even more canonical, it's like some derived category of abelian local systems on BG. Then you don't have to know that you have a base point. You don't have to pick a base point of BG. And then the third will be pairs, so M alpha, where M is now an object in D BG, and alpha is an isomorphism from H0 of M to Z, such that Hi of M equals 0 for I different from 0, 1.
In one, don't you want to assume fibers are BA?
Sorry? Yeah, yes, I do, you're right. Yeah, so thank you. Yeah, because otherwise you could have some non-abelian group, yeah. Yeah, thank you, I should have, yeah, sorry. Right. So fiber should be non-canonically isomorphic to some BA.
Relative H1 is relative.
But you could have...
Yeah, I could have a non-abelian group whose abelianization is trivial. I could have a non-abelian group who's, like take G to be trivial group and take X to be BW, where W has trivial abelianization. Yeah.
You meant it's abelian.
I meant the fiber is BA, non-canonically, but canonically the relative H1 is A with the given action of G. Yeah, thank you very much. Thank you. Yeah. Okay. So, all right, and then this is just by passing to the fiber here. You get an object that only has degree, which is what we did in the proof of Nakayama-Tate. You get something that only has H0 and H1, but the H0 is fixed to be this, and the H1 is fixed to be that. Beta. Yeah. Beta H1M isomorphic to A. Right. You know, I said I'd give 5, right? Yeah, I lied. Yeah, I mean, you could make another. Okay, you could do 5. I'll say it in words. You could say objects are group extensions like this. Morphisms are, morphisms between the group extensions, which are the identity on the outer layers, and 2 morphisms are given by conjugation by something in the abelian subgroup. Okay, so there, I did 5.
What is 0? What is the C?
What is C?
C, the complex C.
C.
Cochain.
Where? Oh yeah, I just mean a group cochain. Yeah. So I said we need a co-cycle level refinement of this. So, but we have that. We have some model for chains of this acting on this. Fix whatever model you prefer, and yeah. So in fact, I have infinitely many. Depending on which model for cochains you choose.
The standard one, you can normalize it, but
Yeah.
this is the only 2 models that usually are used.
Usually, yeah. But if G is cyclic, then you can choose a different model. Yeah. All right. Right. Okay. So this leads to the following definition. So the point is, I want to express what structure we need to actually do this construction canonically. And we shouldn't canonically hope to get a group, because already the Galois group isn't really a group. So we should canonically want to get a groupoid. So anyway, the definition is that, I'll say a refined class formation is a triple. So C, now F instead of A, and then alpha, where, so C is a Galois category, as before. So 2F will be a co-sheaf. I'm going to switch from sheaf to co-sheaf. So it's a co-sheaf on C with values in the derived infinity category, if you like. So, and 3 alpha is a map from H0F to Z, which is an such that. So then the first condition is that hi f of x equals 0 for all I different from 0, 1 for all x in C. So this co-sheaf here only lives in 2 degrees, and then this one is supposed to fix what's going on in the bottom degree. So alpha is an isomorphism when x is connected. Which means that in general, H0F is just going to be the product of the Z, product over the connected components of Z.
What is the co-sheaf axiom?
The co-sheaf axiom is that, so yeah, let me make that more explicit. So 2 means, so that it means that, f of empty set equals 0, f of x disjoint union y. And then if x is connected and G is a group of automorphisms of x, and you take f of x homotopy orbits G, like that maps isomorphically to f of x mod G. So if you take the group hyperhomology of G acting on this complex, it's quasi-isomorphic to this complex.
And how generally this notion of co-sheaf is defined in the...
Well, no, you can define what it means to be a co-sheaf with values in any infinity category. You just have to put disjoint union here instead of...
Okay, but that's in this case where you have group or in more general sites. Okay, you're not just defining it in this.
Yeah, let's say this is exactly what I mean. Although...
So how should we read? Now we have low index I.
Lower index I.
We have HI.
Yeah.
Homology.
Yeah.
Because it's
Well, that's just where the degrees things live in. Remember, we had Nakayama-Tate map was from something in degree 0 to something in degree 2, and you take the shift, and it just lives in those degrees. Has nothing to do with cohomology anymore. It's about this derived object in which.
Yeah, but in derived object they use only the upper indices.
Yeah, I'm sorry, I use lower indices.
Which is a minus upper indices.
Yeah, exactly.
The infinity category with co-limits.
with finite coproducts but you could say that this is positing that the relevant colimits exist. Okay, let me. It's about time for break, but let me state the theorem first, so you guys have something to chew on while you take your break. So theorem, giving a refined class formation, so is the same thing as giving a class formation CA plus extra data. So we want to know what data it takes to promote a class formation to a refined class formation, and it's a map from, I need some notation. So there's a funny group here. So a map in D of Z. Where this group, this is just a subgroup of Q, and it's equal to the union over all objects of 1 over the cardinality of x, z. And cardinality of x means you think of this as the Galois category of finite gamma sets, and you just take the cardinality of the corresponding finite set. So it's the degree of the extension. So the more extensions you have, the more denominators you're allowed. And in examples, this will always just be equal to Q, because you'll always have extensions of whatever degree you like.
And there are no conditions on the map?
Oh, thank you. such that kappa induces. Yeah. Where am I? Okay. Such that kappa induces an isomorphism, so 1 over Cz mod Z is isomorphic to H2C. Okay. Okay, let's, yes. Yes, because this is actually cohomology now. So now, yeah, well, okay, the convention is upper index equals negative lower index, and now I promise I'll be consistent. Okay, we'll take a 5-minute break.
Sorry, and there HIF of x means HI of f applied to x, or HI of f of x?
So yeah, I mean HI of f of x. So what? F of x is an object in that category, which is the derived category of the integers. So there's HI. I could put brackets, but yeah. So there's a corollary. So the two groupoid of promotions of a class formation. So if you have a class formation CA to a refined class formation, so you can analyze what it takes. So the pi 0 is just the set of injections from this H2 group, which is, so to speak, the Brouwer group. You have to put it inside Q mod Z.
Do you speak about the class formation with already specified generators?
No. So this is the data of a so-called invariant map. That's, an injection like that, and that's the same thing as a compatible collection of these UHNs. So the pi 0 level choice is just choice of such generators, as you might naively expect. But there's also pi 1, and pi 1 is given by an X group. So 1 over CZ to the value on the terminal object, the global sections of A, in other words. And there's also a pi 2, potentially, which is a Hom group from the same thing. So if you want to know how canonical things are, you kind of have to contend with not just this choice, which is classical, but also potential ambiguity coming from here, and even potential higher ambiguity coming from here.
But I think that if you work abstractly, so without compatibility assumptions, so that there would be potentially an obstruction to the existence even.
Yes, it took me a while to realize that what I said is to arrive at this simple formulation, but it's correct. Even without countability assumptions, it's still correct.
So the pi zero thing means that every element in pi zero is represented by something in a refined class formation.
Yeah. So in particular, it's non-empty. So you can always do it. Okay. Well, let me give you the idea of the proof.
Sorry, just a question.
Yes.
In what respect does the, maybe it's indicated, I just can't make sense of it. To what extent does the pi 1 or pi 2, depend on the choice of base point?
What base point?
Oh, you mean this is the terminal object of my categories. Everything I wrote is completely canonical.
Okay.
Yeah, well, equals is maybe it's like the general story. This is a torsor for this group. This is a torsor for this. Yeah. Okay, idea of proof. Right. So of this, because the mechanism of the equivalence is going to be important. It's based on something. So the formalism of transfer maps. So if f from C to D of Z, well, really this could be any semi-additive infinity category, which admits orbits and fixed points for all finite groups. Groups G, but let's stick to this example. If this is a co-sheaf, then there exists a canonical pre-sheaf called F-ter, passing the transfers, C op to DZ, with the same values. So in examples, this is kind of given by usual transfer maps that you have in these kinds of situations. Also, so this is in general just a pre-sheaf, not a sheaf, but F-ter will be a sheaf if and only if. So for all x and g, so x is connected, g is a subgroup of automorphisms, the Tate cohomology vanishes, or the transfer map in this form, which is just associated to the g action on f of x, should be an isomorphism. And the Nakayama-Tate lemma implies that this is satisfied if f has uniformly bounded sections, let's say. I.e., there exist A, B, and Z such that hi f of x equals 0 whenever I is not in the interval from A to B for all x and C. So there's a kind of a formal bit, which is you can pass to transfers, and you have this criterion for the pre-sheaf being a sheaf. And then there's the non-formal bit, which comes from Nakayama-Tate, Nakayama-Tate will tell you that if this kind of thing just happens in a band of width at least 2, the isomorphism in a band of width at least 2, then it has to be an isomorphism everywhere. And if you're 0, then you're good. Okay. So then, so in the situation that we're in, yeah, the argument isn't quite as simple as what I just said, but it's still true. Right. So then given your refined class formation, what was it? How did I use? Oh yeah, C F alpha. So then F tur is a sheaf. And then, but it's a sheaf, but it has the same values as F. So also it's a sheaf where the sections only live in degrees 0 and 1. The sections, the derived sheaf whose sections on any open subset or any object only live in degrees 0 and 1. And that implies that when you take H1, section-wise, this is a sheaf of abelian groups. So you call that A. That's the top non-vanishing degree of a derived sheaf is always going to be an ordinary sheaf. Okay, but the H0 is not going to be a sheaf. So the H0, this procedure of passing to transfers is functorial in additive functors. So when you can understand the homology of F tur as just F tur of the homology. And that's so something you could call Z tur. What you get when you take the constant co-sheaf with value Z and ask what the transfers are. And that's not a sheaf, but when you sheafify it, you exactly get the constant sheaf on this thing I called 1 over CZ. So you can embed this non-constant pre-sheaf inside the constant pre-sheaf Q by suitably dividing by the index. And then the sheafification will identify with the subsheaf of this, which is the constant sheaf on this guy where you just allow certain denominators. And then the Postnikov tower of this F tur as a derived sheaf is classified by a map. So you have the sheafified H1, or sorry, the sheafified H0 going to the sheafified H1 with a shift by 2. Because then when you take the fiber, you get something with the right H0 and the right H1. But this corresponds to exactly what I said by a junction. Right. This is obviously quite technical, but I want to make some points. I want to raise some questions about how canonical you can make class field theory, and to do it, I sort of need to get into the weeds. So let's go back to the examples now. Well, let's actually look at Q. This is our primary example, is the class formation for the rational numbers Q. So
Was this the idea of proof of the
No, this was the idea of proof of the theorem. Yeah, the corollary is kind of immediate from the theorem, because you just analyze this space of maps like this. Okay, so the example for Q, so let's look at, so the pi 0 is the usual data. So the inv, so you have to give H2 of GQ Adele class groups. Oh. What is it called? C? Yeah, Adele class groups. Let's call it A. We've been calling it A. In this case, it's going to be an isomorphism to Q mod Z. But I said the usual, but there's actually two conventions which differ by a sign. There's the, yeah. So let's say, but the two conventions correspond to different conventions for the Artin map. So usual Artin map. So there's two conventions for the Artin map. One is that uniformizers go to Frobenius elements, i.e. arithmetic Frobenius elements, i.e. the thing you think of as Frobenius, raising to the pth power or cardinality of the residue field power. And then there's the convention that they go to what for some reason are called geometric Frobenius elements, which is the opposite of that. So you take the inverse of that, the negative of that. I still don't understand why one would ever change Artin's convention. I don't understand why those are called geometric. Probably I'll never understand. In any case, we'll stick with the Artin convention.
No, they are called geometric because when you do a talc, for example, when you do a talc cohomology, the action of Frobenius corresponds to this. I mean, the kind of pullback.
Yeah, but why is cohomology more geometric than homology?
So the pullback on cohomology by raising to the q's power is this action of this guy in the Galois, which is the inverse of the.
Yeah. But it's inconsistent. So first of all, cohomology is not more geometric than homology. If you said the same thing for homology, it would be the opposite. It would argue for the Artin convention. And then why do you call Tate twist weight 2 instead of weight minus 2? Why do you choose a positive? I mean,
Actually, Bruginian showed me a letter from Grothendieck to Manning.
Yeah.
Actually, the only letter written in Russian. And Grothendieck complained that Manning wrote these things about lotus, and he mixed sign for Tate twist for positive to negative.
It's just a convention. Okay, in the end you have to choose a convention. I don't understand why cohomology is more geometric than homology. To me it's the other way around. So geometric Frobenius should be what people call arithmetic Frobenius. Cohomology is more algebraic, whatever. Anyway, never mind, we'll take Artin's convention, but it doesn't matter. It's just a global sign choice in the whole story. Right, okay, so that fixes the pi 0 level data, but we still got pi 1 and pi 2, but it turns out that the x vanishes, so. And the hom is not so big. It identifies with the positive real numbers under multiplication. So the upshot is that there's basically a canonical choice. If this is bugging you, note that you can pass to norm 1 subgroups.
Is it X in the category of Galois? No.
No, it's just abelian groups.
This is just abelian.
Yeah. Because this kappa is a map from this guy to this in D of Z. Because I argued that this is a constant sheaf. So I had to set this up in a clever way to make sure that this worked out simply.
And instead of A, here A is the sheaf still. R gamma C A is. A is our class group sheaf, yeah. Yeah. And then when you take A star, it's just A on the kind of the.
It's the global sections of A.
The sections instead of. Okay, but you know that the H1s are but then the H.
Yeah, it took me. I did have to struggle a bit to find a proof that makes this analysis simple, but this okay. So it's not obvious what I'm saying. Right. So you have a canonical. So you can pass through the norm 1 subgroup, and there's a canonical, like the Adels is canonically like the norm 1 part is canonically the positive reals direct sum. So there's no problem. So here there, on the norm 1 part, there's no choice. This factor goes away. You get 0 and 0, and then you can just direct sum on this thing in degree 1, and it doesn't. And then you get a canonical choice even without the norm 1 thing. So for the rational numbers, there's basically a unique, but in any case, a canonical choice of refined class formation. Now, if F is a number field, then if you do this analysis, well, you'll still get x equals 0, but your Hom group will be noticeably bigger. So it seems there's not really a canonical choice from that perspective, but actually there is. You can just
A is the real direct sum A1, or A1 is A.
I'm sorry.
A1? Oh.
A and A1 should be speaking.
Oh my gosh, yeah, that doesn't look right, does it? Yeah. Yeah, thanks. Yeah. Okay. So in general, if you have any Galois category with a refined class formation and you have a connected object, then the slice category is a Galois category, and you can just restrict the data, and it's obvious from the axioms that it's a refined class formation. So in other words, a class formation on a profinite group induces a class formation, also refined if you want, on any open subgroup. So then we restrict the one from Q. Choice for Q. Then you get a canonical choice of refined class formation for any number field. Okay, now here comes the, the unpleasant surprise. So let's say that, say K is a finite field. Well, let's do a little k because it's finite. So then again, so there's no problem at the pi 0 level because there's just, the group is kind of canonically Q mod Z, the H2 group. But if you calculate the X1 from Q to Z, you get a rather large group, Z hat mod Z. In this case, the Hom is 0. So there exists a refined class formation. It is unique up to isomorphism. The choice of lift is unique up to isomorphism. But the isomorphism is non-unique. So somehow finite fields are worse than number fields. In fact, so you can analyze this and so a choice of K bar gives a refined class formation. An isomorphism from K bar to K bar prime over K gives an isomorphism of refined class formations. But two such induce the same if they differ by Frobenius. So two isomorphisms between algebraic closures will give you the same isomorphism of refined class formations if the isomorphisms differ by a power of Frobenius. So if you want a refined class formation for finite fields, you need to fix an algebraic closure sort of up to Frobenius. So this will be more obvious from the Weil group perspective. So from the Weil group perspective, so we're going to see that refined class formations are basically the same thing as Weil groupoids. But in particular, if you choose an algebraic closure of a finite field, then you get you get to say that the Galois groupoid is this, and then you can write down a canonical BZ mapping to it, and that is the Weil groupoid. So this is Galois groupoid. This is the Weil groupoid. But you can only write this down, like once you choose an algebraic closure to make this B of that group, so that you can then write down B of Z mapping to it. Even though the Z mapping to Z hat is in some sense canonical, you can't really write this situation down canonically without choosing an algebraic closure. Okay. By the way, we can do the same trick as passing from here to here. We could start with k equals fp, fix a choice for fp, then for any finite field, you automatically get a canonical choice, whether or not you embed that finite field in your choice of algebraic closure of fp. Okay. Right, so if k is a non-Archimedean local field, then again, on the pi0 level, we have our canonical system. Here it's actually the same as in the finite field case, z hat mod z, and the hom is 0. So it's just as canonical as on the residue field. And in fact, it's not too difficult to make a one-to-one correspondence between refinements of the class formation for your non-Archimedean local field and refinements of the class formation for the residue field. So once you fix the data for fp, you then get it canonically for all finite fields and then canonically for all non-Archimedean local fields. Okay, what about, there's one, sorry, I want to mention one more thing in this context, which is, there's another way of reinterpreting this data here. So this, in this case, kappa, remember in this case of local fields, our class formation was given by GM. So in this case, kappa is a map from this Galois group with coefficients in GM. This is the same thing as a cocycle for a class in H2 FPQC spec K of GM tilde. This is the protorus with character group Q. So this is also the same thing as a gerb for that protorus, which is the same thing as a Tanakian category. So a Q-graded Tanakian category.
So here it's a big, okay, it's a protorus.
It's a protorus.
And you take cocycle for k sep over k, or cocycle relative to the separable closure of k. Or
Yeah, exactly. As a profinite group, but it's the same thing as the FPQC cohomology of this scheme with coefficients in this FPQC sheaf. I mean, because this guy is homs from this to this. That's the idea. So then you kind of just adjoint it over, but of course you have to check that it's correct. Anyway, a Q-graded Tanakian category. This is called the Kottwitz category, and it's also isocrystals. So, e.g., if k is equal to QP, then it's you take vector spaces over the completion of the maximal unramified extension equipped with a semi-linear Frobenius operator. And the Q grading corresponds to the Dieudonné-Manin classification. Of isocrystals. Right, so in other words, this data that I'm discussing of refinements of the class formation for local class field theory is the same as the data of an actual Tanakian category in the two category of Tanakian categories that gives these isocrystals. And note that this object here depends on the choice of FP bar. The maximal and ramified extension of QP is the same degree of canonicity as the algebraic closure of the residue field. So it's consistent, everything I'm saying. Okay. Where am I? Okay. Right, so Archimedean local field. So
Q-graded Tanakian category, there is some compatibility between Q-grading and the dimensions of object under fiber factor, or like does Q-grading interact with?
Oh yeah, it should be a Q-graded Tanakian category which is locally isomorphic to Q-graded vector spaces. But that's it.
But for example, if instead of GM tilde there was Z, the usual GM, then I would just get kind of Tanakian categories, right? Without any.
No, you get Z graded. I mean, and there's no causal sign here. It's really just.
But would not such things just like classify quasi-coherent, I don't know, shifts of K?
Right, but you can always think of that thing as the degree 1 part of something Z graded.
Oh, okay.
Yeah, because otherwise you don't have a tensor structure, right? I mean, if you have something coming from a Brouwer class,
I understood it.
Okay. Example. Yes. So K Archimedean local field. Okay. So actually here pi 0. There's no choice for the inv map because the H2 is order 2 and there's only one injective homomorphism to Q mod Z. So here actually pi 0 is equal to trivial. So the X. But here it's not Q. Here's one case where it's not Q. So it's really. So if K equals R, say, according to the normalization I chose, it's 1/2 Z, and then R cross, and then HOM, 1/2 Z to R cross. Okay, but this X group is 0 because this is projective, and this HOM group is just R cross. And again, by passing to norm 1, you can reduce this ambiguity to a plus or minus 1. So in the Archimedean case, there is a refined class formation which is unique up to isomorphism, and the isomorphism is unique up to sign. So there's a way to understand this. So refined class formation is the same thing as fixing fix a choice of H in the Brouwer 2 groupoid. So if you believe the complex numbers are canonical, or if you believe the quaternions are canonical, then there's no choices here. But if you believe that only R is canonical and the rest is kind of convention, then what you have to fix is the class of the quaternions in the Brouwer 2 groupoid. It's the exact same data as what you see here.
So the Brouwer 2 groupoid is the...
Central simple algebras are the objects, Morita equivalences are the isomorphisms, and natural isomorphisms between Morita equivalences are the two morphisms. Yeah. Okay, and again, you could think of this in terms of Tanakian categories, so a 1/2 Z graded Tanakian category, and it's this, again, so-called Kottwitz category, whose study was reinvigorated by Peter Schulze in his ICM address, the study of these Kottwitz categories, local and global. We haven't, okay. All right. So, yes, I should also mention when I was discussing the number field case, when we were discussing class formations, we also had a number field case with restricted ramification given by some set of places. Again, if you fix a refined class formation for F, then for any set of places you get an induced refined class formation for number fields unramified outside S. So you also have a canonical choice there with a restricted ramification. So the only choices you need to make all of this data is you need to choose an algebraic closure of fp for every prime p, and if you like, you have to fix what you mean by the quaternions. Or you could fix C, that also determines a choice. Fix an algebraic closure of R, that also determines a choice. Okay. So
in this thing with Q going to R gamma C, K, GM and cocycles,
Yeah.
so when K is of pure characteristic P, you have to distinguish algebraic and separable closure. And when you take the tensor product, it's not, you don't have P through, I mean, this if you work with, because this Q involves also P its roots. And so when you have to look at GM tilde torsor from tensor product, like they're trivial, you get into some trouble.
yeah, you might be right about that. I should probably stick to characteristic 0 for
Yeah,
this.
so I think it could be that in some sense you are right, but you have to think about what you are exactly saying.
Yeah, I completely agree with you. Thanks. Yeah. All right. So, we also have to. So we talked about class formations and refined class formations for global and local fields, but one thing we haven't discussed yet is the problem of local-global compatibility, which is quite non-trivial. So if you thought that was technical, just wait. So definition, so a map of refined class formations is, so you have to give the following data. So the first thing you should give is a pullback functor. So an exact functor from this Galois category to this Galois category, which tells you how to pull back. And the second thing is you have to give a map from the push forward of this co-sheaf to this co-sheaf, which intertwines alpha and alpha prime. So hereby, the push forward of a co-sheaf or a sheaf, I just mean the composition. Co-sheaf is just a functor and push forward is just composition. And it'll send co-sheaves to co-sheaves and sheaves to sheaves because of the exactness here. Exactness means it preserves finite colimits and finite limits. And it's quite technical to analyze. I'm going to skip the technical details of analyzing morphisms of refined class formations, and I'll just say an upshot. Under some Ri lim vanishing assumption, so if you're given this part of the data and the corresponding thing for the sheaves, like on the class groups, are given, and let's say that this corresponds to a surjective map of profinite groups, so a quotient of profinite groups, which implies that this push-forward functor is exact. And then we need a compatibility on the associated invariant maps. So you take the invariant map, which is defined on H2C with coefficients in A, maps to Q mod Z. And on the other hand, you have the invariant map C prime, A prime, into H mod Z. And then we have C prime F lower star of A. Then there are maps like this, and you have to require that the diagram commutes. So this, I guess this is just that. Then there exists a map of refined class formations, which is unique up to isomorphism. But the isomorphisms, the set of isomorphisms will be in bijection with, again, some Hom group. And then you'll have some inverse limit of values. So I don't want to be, oh wait, I might have A and A prime mixed here. So C and then A prime, yeah. Anyway, you have to make some more analysis about this. But the upshot is that if F is a number field and V is a place of F, then there exists a map of refined class formations. Wait, just a second. Did I say unique up to isomorphism? Oh, I should have. Wait. Yeah. There exists a map of refined class formations for the so the refined class formation for F nu going to the refined class formation for F. And it's unique up to isomorphism, but it's not kind of uniquely specified, so we also need to make that choice for every place. So make a choice for F equals Q, and this induces choices for all F. And let me make a remark. Again, I won't go into all the details, but the choice of this map refined class formation for F for all nu is equivalent to the choice of global Kottwitz gerb plus local global compatibility. So the from the in refined class formations, globally it's canonical. Locally it's okay, but in the local case, choice of refined class formations and choice of Kottwitz gerb are equivalent. In the global case, they're not. Global class formation is canonical. Global Kottwitz category is not canonical. But if you give the global thing together with the local global maps, doing that for either of the two theories is the same. And in fact, if you take this, well, if you take this, it's kind of, if you take the data you get from the maps of refined class formations, direct sum over all places, make a small modification to make it a delic, and then somehow you can pass to the fiber, and that gives you the Kottwitz gerb. Where? This, the Kottwitz gerb is this gerb representing this class in the local case. I didn't explain what it is in the global case, but it comes out of these maps.
So, by the way, it's a little strange because there is no 2 in the first row. 2? You want something in H2.
Where?
No, you want H2 spec KGM tilde. So why in the first line you have R gamma SC?
Oh, well, that's just because I forgot to put the 2. Yeah. I mean, the data, according to the theorem, the data of how to refine a class formation is exactly this data. Yeah, that was my mistake. Okay, so I think I haven't really gotten to Weil groups. But I want to say something. This is annoyingly technical. All of this, producing this data, these refined class formations, it feels quite annoying, especially because you do have to make these non-canonical choices at various points for finite fields, and then also in choosing the local global compatibility map, you have to make non-canonical choices. So wouldn't it be nice if there were a canonical way of doing things? So here's I'll state it provocatively as a question, yeah. So, does there exist a canonical, sorry, definition. So, let me define a number ring. So this will be the category of number rings is the category of locally compact Hausdorff rings, which appear in number theory. So global fields, local fields, finite fields, rings of integers, whatever you like, those kinds of, just to, does there exist a canonical functor F, so like a universal refined class formation. So Cauchy. Cauchy. Yeah, I'm getting confused about my ops perhaps. No. Yeah, no, this is right. Okay. Plus an isomorphism such that, so one is that hi f of r equals 0 for I different from 0, 1 for all f. The second thing is that h1f r is the usual class group. So for a local field, the ring of units, for a finite field, Z, for a global field, Adels. And 3, it gives a co-sheaf on the finite étale site of any R. Okay, it should be op. I just realized. Right. And then 4, so induces class field theory on all R. This is a property. So the structure would simple structure. Just for every number ring, you give a complex of abelian groups whose homology is only in 2 consecutive degrees. The H0 is Z. But you do it functorially, and you make sure the first homology is the class group. Just do that, and you automatically get all of class field theory together with the refinements that I've been discussing. Just 100% for free. So I'll make a remark. So I was able to figure out what H1, kind of a definition of H1, which is a K1 group of locally compact R modules. That gives the correct class group in all examples. So for a global field, it gives the Adel class group. For a local field, it gives the multiplicative group. For a finite field, it gives Z. But the K0 is not usually Z. So So some modification will be necessary if you want to truly recover class field theory in a canonical way. So I pose this as a challenge. I mean, really everything, the world is supposed to be simple, right? We shouldn't have to do this crazy homological analysis to produce like the most important structure you have in number fields and local fields and the relationships between them. Like there should be some canonical choice. But of course, for a finite field, if you just restrict to finite fields, I'm kind of saying there should be a canonical choice of FP bar, at least up to Frobenius. And whether you believe that or not, I don't even believe that. But wouldn't it be nice? So I'll leave that as a. No, I've got a few more minutes, so we can.
So in this remark, higher ki is also very big. Well,
Excuse me?
like if I take ki for I greater or equal, like I can't. Sorry, this is also to d of z, not to spectra. Never mind.
Yeah, but it could be to spectra because it doesn't matter when they're just in consecutive degrees. So the truncation of the K-theory was a possibility that just doesn't work. Of course, you'd have to check it's a cosheaf. I'm not saying that's easy. Even when you truncate that it's a cosheaf. I mean, before you truncate, it's also not a cosheaf. I mean, nothing is going to be obvious, but at least I want a way to just produce all the relevant structure. Okay, and then checking the axioms. Okay, maybe that's hard. Fine, but the structure should be given. Okay. So Weil groups, or Weil groupoids, so if C is C gamma with gamma finite, the story is simple. A refined class formation, as I tried to motivate at the beginning, it's just a certain kind of abelian gerb. On B gamma. And that can be viewed as a groupoid. Well, let's call it W, mapping to B gamma, such that fiber is isomorphic to BA. Non-canonically, but when you take homology, then it becomes canonical. So this is the Weil groupoid. So we indeed, so I didn't explain to you how to go between the different interpretations of gerb, but well, going from this to this is not so bad. So given an abelian gerb, you instead of just looking at the relative h1, you look at the relative chains and you truncate to degrees 0 and 1. Then in degree 0 you'll get z, and in degree 1 you'll get a, but there's still a non-trivial twist, an extension class that glues the h0 to the h1, and that is exactly what corresponds to the same data describing the gerb. For a general C, so C is maybe non-canonically equivalent to C gamma, where this is just a profinite group. Then a refined class formation on C is the same thing as a compatible system of refined class formations on the finite quotients. That's actually obvious from the definition. If you have I should say like n, gamma mod n. So all the quotient groups of your profinite group, they correspond to Galois full subcategories of your Galois category. Just if your Galois category is all finite separable extensions, then you just look at finite separable extensions which are dominated by some fixed Galois cover, which can be dominated by some fixed Galois cover. And then giving a functor out of the full Galois category is just the same thing as giving compatible functors on all the finite levels. And that's, that's just the Cauchy, and the Cauchy property is checked at every finite level. So, but you'd want to, and then, so the transition maps, then you'd want to understand what the transition maps are in terms of these abelian gerbs. So the transition maps, so if you have like gamma going to gamma prime, or B gamma goes to B gamma prime more canonically, and you have W and you have W prime, script W and script W prime, then this guy is determined by this guy. This guy is the abelianization of the composition. W goes to B gamma prime. So if you have something where the pi 0 is a base point, pi 1 is arbitrary, then you can abelianize it, which has the effect of abelianization on the pi 1. And that's the procedure you have to go from here to here. So you get a tower, or not a tower, but an n-index system of Weil groupoids. And then you want to take this to be the inverse limit. So corresponding to each of these refined class formations for a finite group, you have this gerb living over the finite group. Let's call that Wn. Those form an inverse system where the transition maps are this abelianization map that I discussed. And you want to take the inverse limit.
Okay, and then you have a problem of choosing compatibility.
Exactly. Then you need to, exactly. Need to show, if you want a group, you need to show that pi 0 of W is trivial. And, well, actually, that's exactly what you need to show, that the pi 0 is trivial.
In particular, non-empty.
Yeah, in particular, non-empty. So we will continue the discussion next time, because this comes from a compactness argument, as Ofer already hinted.
Okay, so I confused different parts of because I was familiar with some more. So here you have some abstract thing which avoids this issue, and then you put it.
I put it at the very end, yeah. Okay. Now, but yes, so tomorrow, picking up next time, you can actually forget a great deal of the technical homological algebra we discussed today. I'll start over with condensed groups, like how to view locally compact Hausdorff groups as condensed groups, and basic things about that, and then we'll discuss the Weil groups, Weil groupoids, prove why this kind of thing, how you can control this kind of thing, and then we'll have a different perspective on refined class formations. There'll just be certain kinds of Weil groupoids, and it'll be a little bit easier to discuss.
About truncation in certain 2 degrees that I didn't. What was the thing you mentioned there about truncation or something that you get Z and A in this?
Well, the whole magic of this notion of class formation or refined class formation is that you have like the derived sheaf or co-sheaf property. So you have, in principle, you have homotopy fixed points for finite groups floating around. I mean, you have cohomology of finite groups floating around, but nonetheless, all of the sections are concentrated in 2 consecutive degrees. When you take sections of this sheaf on anything, it lives in 2 consecutive degrees. But yet, it's a sheaf and a co-sheaf at the same time. So when you take fixed points of that thing lives in 2 consecutive degrees, it lives in the same 2 consecutive degrees. So this is kind of like the Nakayama-Tate lemma, if you think about it. And that's the whole magic of the situation. That's why you get so many different consequences and so many different interpretations of everything, because, it's just, there's cancellation somehow. In principle, the group cohomology of this guy and the cohomology of this guy contribute, but most of it just cancels. And you're left with something quite simple, even at the end.
Or maybe it was about the relation between 2-term, this original derived category and the gerb and the...
Oh yeah, there was something, a 2-term object in the derived category with H0 fixed to be Z and H1 fixed to be some abelian group. That's the same thing as an abelian gerb. The functor in one direction, the functor from abelian gerbs to those objects just takes the relative homology, but truncated to degrees 0 and 1.
The relative homology.
Yeah, relative chains as an object in the derived category. So you have some x, you have some w mapping to b gamma, you take relative homology, but it's really a chain level object. And it might have higher homology, but you just forget about it. You truncate.
Okay, so, okay. Relative chains.
Yeah.
Okay, and then after you have defined something, then to check it, then you can use some.
Then you just calculate that it's an equivalence, yeah. You can also write the functor backwards. But okay.
Of course, there is a classical way to do it, which is a bit puzzling because you work with cocycles,
yeah,
and then you the extensions x2 is the point is that x2 is by derived function is some group cohomology, but extensions of groups. This is very classical thing. You have a cocycle description of extension of group. You get a cocycle, which is also used to calculate the right factor. I mean the complex.
Oh, okay.
Change used to calculate the right factor. So this is the kind of puzzling way, which is summed by the classical way.
Yeah.
The bit is not. You don't understand the.
Yeah, but it's nice in this perspective. You really can write mutually inverse functors, identifying these two groupoids. Like you can just write down functors implementing these. I was saying there all these two groupoids are equivalent. I mean, for the ones that were one where you say chains and whatever, who cares? But the ones that were actually some meaningful object, like this kind of thing, or object in derived category, you have functors implementing the equivalences between these two groupoids, explicit functors. So it's not just like you hands-on check that the two groupoids are equivalent. There's really a natural explanation. Okay.